we will start with explaining the idea behind the cache memory. If you already are familiar with that, you can just skip this video after a few seconds. After cache memories, I will explain the most simple memory consistency model, sequential consistency, and then explain. I will not explain it in this video, but in a later one, and then explain how the hardware can implement this memory consistency model so that the hardware behaves as it should, given the guarantees that the consistency model gives to the programmer. Okay, and then we will identify some performance defects with sequential consistency and consider removing this, how to remove them. And then we will go into so-called relaxed memory models. And the two most important are weak ordering and release consistency. Weak ordering was invented by Michel Dubois at the University of Southern California in Los Angeles, and release consistency by Kourosh Garoshello at Stanford University, where he did his PhD on in the Dash project, Stanford Dash machine. Okay, so if you already know about cache memories, you can skip the rest of this video. So what I will do now is to explain the idea of a cache. And I will use hardware described as a C program. Okay, and if we have a simple CPU, it could look like this, that we have not a class, since there are no classes, but a struct. And this type def just says that this struct will be called that. So the type will be that, but that's not very important. Okay, and this CPU, it has an array of 32 registers and a program counter which contains the address of the next instruction to execute. Then here is the cache. It is ridiculously small, only 8 elements. Usually a cache near the, in the CPU chip is much larger. Otherwise it would not give much performance improvement. The smallest reasonable cache is perhaps 32 kilobytes. Okay, so what does this cache consist of? It's a number of elements, in this case 8, and each element has data and an address. There is also a valid attribute which says that this address is valid. I mean, there must be something stored there. Okay, and well, what are we going to do with this? The CPU will request, if it reads, it will request data from memory, but instead it looks and checks if this address is present in some of these rows, and also that the valid is true. Then it can take the data from there instead. So this will save a lot of time, and it is exactly the same thing that we have things on our desk instead of having to go to some shelf to get them every time. So on the desk we store the most frequently used items that we need for work, and the same for a CPU. So the address, where does it come from? Well, it is the compiler that either gives it the exact address, such as a constant such as 293 or something in other bases, or it could be an offset, a constant added to a register. But let's say that we are using a global variable so that the compiler has decided it should have this address, for instance. Okay, so to use the cache, we have to find this address and also that the valid is true. And if it can find it, then we say it's a cache hit. If we didn't find it, it's a cache miss. And this can easily save us 100 clock cycles or more. The bigger the machine, the more number of clock cycles are expected to be saved. By bigger, I mean if there are a very large number of cores and they can be connected in some topology looking, for instance, like a chessboard. Then the data must be fetched from perhaps a different corner of the chessboard, and that will take far more than 100 clock cycles. So what we see here is C code to simulate a simple machine, and we see the case for doing a load instruction. It doesn't, and there is one case for each instruction type. So we will not use that in the course, but those who are interested can look at the file machine.c in the Treasury directory. But well, you can look at there if you want to. But when the machine wants to execute this load instruction, it first computes the address as a sum here, and these come from a register value and a constant in this case. And then there is a loop which goes through the cache and hopefully finds the data, I mean the address, and then it takes the data from that entry. Okay, it's very important to see that this is not a loop in the hardware. Instead, it is duplicated. But then you may think that this would be very expensive, since there would be hardware to compare the addresses, and if there are like, for instance, 64 kilobyte, there would be a huge number of such comparators. That is done in a different way, but this is the essence of it. You can read a course on computer architecture or efficiency where this is explained in more detail. But this is good enough, and keep in mind it is not a real loop in reality, and there is not a huge number of such hardware to make the comparisons. So okay, if we don't find the data, then we have to read it from memory, and when we read it from memory, we have to typically replace, I mean we have to throw away something else that is already there, and this is called cache replacement. And we only write back to memory if the data was modified, but to make this model simpler, we always copy it back. Okay, so if the data was not found, meaning the address was not found, then we select one row, and if this row had valid data, we save it to memory. But we don't, in reality, we wouldn't do that if it has not been modified. But in our simple cache, we don't note that we have modified the data or not. So we copy it back to be safe. Okay, so then we read from memory. Okay, so what we can see here is that memory is just an array, and it's indexed by this address that the CPU wanted to have. Okay, and then we store the data in the cache. And the same is similar for writing to memory or writing to the cache. So then, an important difference obviously is that we already have the data and we want to put it in the cache. So first we see if the previous version of this data is in the cache. In that case, we just overwrite it and forget the old value. If we found it, then we are done. If we didn't find it, we again select the row, copy back the old contents and write here. So next time that we want to read or write this variable, it's likely to be found in the cache, and we save time. And again, the loop doesn't exist. In hardware, the loop is run in parallel, and there are tricks to make this practical. So it's only one row that may have the data, and that row says, okay, here it is, and and the others just keep silent. Okay. So what we have seen so far is how a simple cache memory works. But we need to look at one more thing, namely something called the cache block. That is relevant in particular for multiprocessors and multi-core programming. So our cache only fetches one int from memory, or 4 bytes for instance, at the miss. And it would be much better, almost always, to fetch, for instance, 8 or 16 ints at a time. Why? Well, if we go through an array, we typically iterate through it, and if we get the miss at the first element and fetch 16 array elements, then the next 15 will get hits. So we save time. And the number of bytes that we transfer to or from memory is called the cache block size. And what is a reasonable cache block size? Well, it is different for single-threaded and multi-threaded programs. I mean, what is best? Because of course, the cache block size is fixed in the hardware. So it doesn't, I mean, we cannot change it depending on how many threads we have. But there is a risk with multi-threaded programs that different threads accidentally have decided to modify data in the same cache block. And that typically disturbs them a lot. We will come to this later in the course and see much more details about it. But that is something to think about, that it's not only one int, and also when a cache block is modified by one thread, then the CPU or cache for where that thread is running will be the owner of that cache block. And it's not only the int that it wrote, but it's the entire cache block that it will own for a while. So if two different threads want to modify X and Y, which happen to be in the same cache block, then they will get ownership of this cache block like a ping pong match, and it will degrade performance a lot. So, okay, that's very important to consider how to avoid.